Hello everyone, and welcome back to some more remote learning. In today's example video, we're going to go over implicit differentiation. Now, so far when we've been working with derivatives, we've been working with explicit functions. Functions where we have some dependent variable equal to some combination of operations with our independent variable. Whether that was y equals some linear, well, mx plus b, y equals some polynomial, y equals some trig function of x, you can see that dependent variable y was in terms of our independent variable x. In this worksheet, we're going to learn all about how to differentiate an implicit function, where our dependent and independent variable are mixed throughout our equation, not necessarily on separate sides and not just explicitly defined. So let's first take a look at the explicit function y equals 3x squared. Let's go ahead and take the derivative of y equals 3x squared. Well, we know the derivative of y equals 3x squared is dy dx equals 6x. Now, something we might not have really talked about is that when we're taking the derivative with respect to x, d dx, we don't just take the derivative of one side of our equation, we're actually taking the derivative of both sides. The derivative of y with respect to x is that dy dx, and the derivative of that 3x squared was that 6x. But let's say that our function isn't in terms of x. Let's say our function is actually in terms of y. So we have some x equals, but we still want to take the derivative with respect to x. We still want d dx. So let's go ahead and take that original y equals 3x squared and solve for x. So if I take y equals 3x squared and solve for x, I'll divide both sides by 3, and then I'll take the square root. So x is going to be equal to the square root of y over 3. Now I'm still taking the derivative with respect to x, not the derivative with respect to y. Y is not my independent variable. X is that variable I'm taking the derivative with respect to. So I'm going to take the derivative with respect to x of x, and I'm also going to take the derivative with respect to x of the square root of y over 3. Or this might be easier to think of as y over 3 to the 1/2. Now we know how to take the derivative of x with respect to x. That's simply 1. Now we're going to take the derivative with respect to x of our right-hand side of the equation, y over 3 to the 1/2. How do we take that derivative? Well, it's going to be a little bit of chain rule, right? We have y over 3, which is some function raised to the 1/2. So what I'm going to do is I'm going to bring my 1/2 down in front. I still have my same inner function y over 3, but now that becomes to the negative 1/2. But with the chain rule, we also have to multiply by the derivative of the inside function. So this gets multiplied still by the derivative with respect to x of y over 3. And that's what we need to think about. How do you take the derivative of y over 3? Well, constant multiple rule. Pull that 1/3 out in front. What's the derivative of y with respect to x? That's dy dx. So right now we have 1 is equal to, I'm going to write that negative exponent as a positive in my denominator. This will be 1 over 2 times the square root of y over 3. That was my y over 3 to the negative 1/2. I bumped it down into my denominator. And this is all multiplied by 1/3 times dy dx, that derivative of y with respect to x. Now what I want to know is what the derivative is. So I want to isolate that dy dx. How do I do that? Move everything that's with it to the other side of the equation. And because it's multiplied by everything, in order to get rid of those fractions, I will multiply. So I'm going to multiply by 2 times 3 times root y over 3, which is 6 root y over 3. When I multiply that to both sides, I'll get 6 root y over 3 is going to be equal to dy dx. And again, that's because when I multiply by 6 root y over 3 to both sides, that canceled out that fraction. Now, this 6 root y over 3 doesn't look as easy as that 6x that we got originally. But what is y? Y is that 3x squared. So if I was to plug 3x squared right on in for y, I would have 6 times the square root of 3x squared over 3 equals that derivative of y with respect to x. My 3's would cancel out. The square root of x squared is x. So this leaves me with dy dx is equal to 6x. So you can see we get that same exact thing that we originally got for our derivative. The important part, the note not to forget, is that when we're doing implicit differentiation, because y is a function of x, we always have to treat that y like the chain rule. So even if we had, let's say, y squared, and we were taking the derivative of that with respect to x, we still need to apply the chain rule. The outermost function is that function squared. So that 2 will come down times y, and our exponent will be decreased by 1. But remember, y is some function of x. So when we multiply by the derivative of that inside function, the derivative of y, that's dy dx. So the derivative of y squared with respect to x is 2y times dy dx. And we'll get more practices with this later, but this is just an important concept not to forget. Now let's continue on, and let's do one more example dealing with this explicit formula that we were originally given. Now, as opposed to solving for x, let's solve for x squared. And that's simply by dividing by 3. So we're going to have that x squared is equal to y over 3. Now if I was to take the derivative of both sides at this point, with respect to x still, the derivative of x squared with respect to x is going to equal the derivative of y over 3 with respect to x. The derivative of x squared is 2x, and that's going to be equal to, and again, it's just 2x, not 2x times something else. We don't have to do the chain rule with this one because we're taking the derivative with respect to that variable. And then taking the derivative of that right-hand side, pulling that 1/3 out in front, what's the derivative of y? Well, that's dy dx, the derivative of y with respect to x. So multiplying both sides by 3, we again get that 6x is equal to dy dx. So what I'm trying to show from these 3 quick parts is that you can take the derivative at any step along your function and still get that same result, as long as you pay attention to the chain rule and remember that y is a function of x. So when you take the derivative of y, you're going to have dy dx somewhere involved. However, obviously for this case, it was so much easier just to take the derivative normally, but in some cases it's easier to work with the implicit function. Let's take a look at example 1 below. In example 1, we're going to use implicit differentiation to find the equation of the tangent line or lines for each of the following. Let's look at example A. So looking at example A, we have y squared minus 6y plus 5 equals 2x minus 3. Now, if I were to try to solve this and make it an explicit formula, it'd be rather difficult, especially since I have y to a power of 2 and then y to a power of 1. So implicit differentiation is going to be the way to go with this problem. Now, in order to find the equation of a tangent line, what do we need? We need a point, and then we need the slope at that point. So we're going to need to find the point, and we're going to need to find the derivative at that point, because the derivative at that point will give us the slope. Then we'll use both of those, plug it into point-slope form, and get our equation. Let's start by finding the point. So we know that x equals 0, so let's solve for y. If I were to plug 0 in for x, I would get that y squared minus 6y plus 5 equals 2 times 0, which is 0 minus 3. So I have y squared minus 6y plus 5 equals a negative 3. This looks pretty close to quadratic, so let's go ahead and set this all equal to 0, which I'll do by adding 3 to the other side. So when I add 3 to the other side of my equation, I'll get that y squared minus 6y plus 8 equals 0. Now let's factor it. What multiplies to give me 8 and adds to give me a negative 6? That's going to be a negative 2 and a negative 4. So I'm going to have y minus 2 and y minus 4. So really, y is either going to be equal to a positive 2 or a positive 4 when x equals 0. So I don't just have one point, I have 2 points that I need to find the tangent line of, because when I have an x value of 0, I have 2 separate function values. So I have the point 0, 2 and the point 0, 4, which I need to find the tangent lines for. So now that I have my 2 points, what do I need? I need the slope at each of those points. So what I'm going to do is find the derivative. And how are we going to do that? Implicitly. So the derivative of my left side of my equation first is going to be the derivative of y squared minus the derivative of 6y plus the derivative of 5, all with respect to x. And remember, when we're taking the derivative of some other variable with respect to x, or as long as we're not taking the derivative with respect to the same variable, then we're going to need to remember the chain rule. So the derivative of y squared is going to be 2y times dy dx, because if this was some function of x and it was squared, well, that derivative becomes 2 times f of x multiplied by f prime of x. So in this case, 2 times y times dy dx. Now we're going to take the derivative of negative 6y, which is going to be, pulling that 6 out in front, it's going to be minus 6 times the derivative of y, dy dx. And then we're adding that to the derivative of 5, derivative of constant, just 0, regardless of what variable you're taking the derivative with respect to. And then the derivative of 2x is simply 2, and the derivative of, again, a constant is 0. Now remember, what I'm trying to solve for is my derivative so that I can get my slope for each of my tangent lines. So if I'm trying to solve for dy dx, because it's in both terms, I will pull that out of each of my terms. So I'm going to have that dy dx is multiplied by 2y minus 6, and that's all equivalent to 2. So you can see all I did was I took dy dx, which was my common term, and pulled it out in front because I want to solve for dy dx. So when I do that, I have dy dx times 2y minus 6. And if I'm solving for dy dx, now that I have it multiplied by everything, I'll just divide by everything else. So dy dx is going to be equal to 2 divided by 2y minus 6. So I have my point and I have my derivative. I just need to find the derivative at that point. So the first one I'm going to find is the derivative at 0, 2, and then I'm going to find the derivative at 0, 4. And these are going to be different slopes because, look at this, my derivative is in terms of y, so as opposed to plugging in x values like we normally do, we're going to need to plug those y values right on in. So for my first one, the derivative of y with respect to x of the point 0, 2, that's going to be 2 over 2 times 2 minus 6. That's going to be 2 over 4 minus 6, 2 over a negative 2, which leaves me with a negative 1. My other derivative, dy dx, of the point 0, 4, is going to be 2 over 2 times 4 minus 6, which 2 over 8 minus 6, 2 over 2, that's going to be a positive 1. My slope is negative 1 for the point 0, 2 and positive 1 for the point 0, 4. So finishing out the equations of my tangent line, I'll do the first point, 0, 2. I'll have y minus 2 equals my slope m, which is a negative 1, times x minus x1, x1 0, so I'll just leave that as a negative 1x. And then my other one is going to be y minus y1 of 4 equals my slope m of a positive 1 times x minus x1, x minus 0 is just x. Two different equations for a tangent line at the point when x is equal to 0, because I had two separate function values. Let's move on to part B. In part B, we have x squared plus y squared equals 16. Now, if we were to try to write this explicitly, we'd be dealing with a square root, and then we'd have to take into account that positive square root and the negative square root for each of these. However, if you don't realize it, and maybe we haven't talked about it yet, x squared plus y squared equals 16 is a circle with a radius of 4. X squared plus y squared equals r squared. So we have some circle centered at the point 0, 0 with a radius of 4. It's just kind of neat to think about all of this. So if we're centered at 0, 0 and our x value is 4, well, we only have one tangent line to try to figure out. But let's just think logically about it. What do you think that tangent line is going to be? That slope is going to be undefined, so we're going to have some vertical tangent line. And let's see what happens when we differentiate this implicitly. So taking the derivative of x squared with respect to x, that becomes 2x, and taking the derivative of y squared with respect to x becomes 2y times that derivative of the inside, dy dx. And that's all equal to the derivative of 16, which is 0. Now I'll subtract 2x from both sides, so I'll get 2y dy dx equals a negative 2x, and then I'll divide by 2y to isolate my dy dx. So I'll get that the derivative of y with respect to x is going to be equal to negative x over y. Now remember, for a tangent line, I need the slope at the point and I need the point itself. So when x equals 4, what is my y value? When x equals 4, I'll have that 4 squared plus y squared equals 16. So I'll have that 16 plus y squared equals 16. Subtracting 16 from both sides, I'll get that y squared equals 0. And the only way to solve this, taking that square root, means that y is indeed 0. And what can we not divide by? We cannot divide by a 0. So when we go to try to plug in that y value of our point into our derivative, we're going to get undefined. So we have a vertical tangent line. And that vertical tangent line occurs at x equals 4. So now that we've got a good introduction to taking the derivative of implicit functions, let's continue to practice. And just like when we did those trig derivatives, all other differentiation rules apply. The constant rule, power rule, constant multiple rule, sum rule, chain rule, those trig derivatives, we can do it all with implicit differentiation. So taking the derivative in part A with respect to x, and I'll be sure to note on the worksheet that we're taking the derivative with respect to x for all of these parts in example 2. So we're essentially finding dy dx for each of these. So taking the derivative in part A with respect to x, let's take a look. The square root of y is like y to the 1/2. So bring that exponent down in front, we'll have 1/2 times y to the negative 1/2, decreasing that exponent by 1. But remember, y is a function of x, so we have to apply the chain rule here. So multiplying by the derivative of our inside function, multiplying by the derivative of y, that's going to be dy dx. And then we add that to 2x to the 4th. The derivative of that with respect to x is going to be 8x cubed, and that's all equal to, what's the derivative of 3? 0. Now we're trying to find dy dx, so we're going to isolate it. And we'll do so by subtracting 8x cubed from both sides. Once we do that, we have dy dx multiplied to everything on our left-hand side of the equation, so we'll be able to divide by everything it's multiplied to. So let me write this out. I'll have 1/2 y to the negative 1/2, or I'll write this as 1 over 2 root y, and that's multiplied by dy dx, and that's equal to negative 8x cubed. So what I'll do now is I'll multiply both sides of my equation by 2 root y. And when I do so, my 1 over 2 root y cancels out so that I isolate that dy dx. So dy dx is equal to negative 16 x cubed root y. Negative 16 x cubed times the square root of y. And all I did at that last step was combine my negative 8 and 2. Let's move on to part B. Part B, we're again taking the derivative with respect to x, trying to find dy dx. So the derivative of x to the fifth with respect to x is 5x to the fourth, plus the derivative of 3x with respect to x is 3, and the derivative of e to the y, well, let's think back to that chain rule for e to the function. Remember, the derivative of e to the f of x, when we're taking the derivative with respect to x, is e to the f of x times f prime of x. So if I'm taking the derivative of e to the y, that's going to be e to the y times the derivative of y dy dx. And sometimes, just as a note, you may want to write y as f of x, like I did over here. That's perfectly fine to write that in your equation, writing y as f of x so you don't forget that it's a function of x. Or sometimes, if you want to leave it as y, as opposed to writing dy dx out, you could just write shorthand y prime. That's something else that I find very common. However, when I'm writing this out, especially on a worksheet, y prime sometimes looks like y to the first, and I just don't want to confuse you, so I'm going to continue to write dy dx, but feel free to shorthand this. So the shorthand of that right-hand side would have been e to the y times y prime. And remember, what are we solving for? Dy dx. I have dy dx only on one side of my equation, and it's multiplied by everything. So all I have to do is divide by e to the y to isolate it. So I'm going to have that dy dx is equal to 5x to the fourth plus 3 all over e to the y. And that's my derivative of y with respect to x. Let's continue that derivative in part C. So we have the sine of x plus the cosine of y is equal to y cubed. So derivative of sine of x is going to be a positive cosine of x. Derivative of cosine of y, remembering that chain rule, the derivative of cosine of f of x goes to a negative sine of f of x times f prime of x. So this becomes a negative sine of y times y prime, or dy dx. And that's all equal to, what's the derivative of y cubed? Treat it like a chain rule. Some function cubed will have 3 times that function, now squared, when we decrease that exponent by 1, but we have to remember to multiply by the derivative of that function, which is dy dx. Now in this case, my dy dx isn't on the same side of the equation, and I want it to be so that I can pull it out of all my terms and then divide by everything else. So I'm going to move this negative sine of y dy dx to the other side of my equation. So I'm going to have that the cosine of x is equal to 3y squared times dy dx. In order to get rid of that minus sine of y dy dx, I added it. So I'll add sine of y dy dx. Now pulling dy dx out of both my terms, you can see they'll get canceled out to leave me with 3y squared plus sine of y when I pull dy dx out. So 3y squared plus sine of y is what I'm now dividing by. So for my final solution, I'll get that dy dx equals the cosine of x all over what was multiplied to that dy dx, which was 3y squared plus the sine of y. So hopefully you guys are getting even more into the hang of this implicit differentiation. Let's do another example. In this one, we have x times y plus 4x minus 1 squared equals x minus 2 over y plus 3. We have y in two separate parts of our equation, and it looks pretty messy. But stick with me, and we'll work through this together. We have to take the derivative of, we'll work left to right. So that first term is x times y. This is actually the product rule. So we'll have first, which is x, times the derivative of our second, dy dx, plus second, which is y, times the derivative of our first, the derivative of x, which is 1. Now that will get added to 4x minus 1 squared. As opposed to expanding that binomial out, we're going to do the chain rule. So bring that exponent down, and then decrease it by 1. So we'll have 2 times 4x minus 1, and then we multiply by the derivative of the inside, which is going to be 4. And that's all equal to, well, you saw that we can do the product rule. We can also do the quotient rule. Low d high minus high d low all over low squared. So low is y plus 3 times the derivative of my high, which is going to leave me with 1, minus high, that's x minus 2, times the derivative of y plus 3 is going to be dy dx. Because 3 is a constant and goes to 0, the derivative of y is dy dx, and that's all over y plus 3, that denominator, squared. Now from here, this looks a little messy because we want to isolate dy dx, but it's really just algebra from there. So let's go ahead and simplify this problem down a bit, and then I'm going to get all of my dy dx's on the same side of my equation and everything that doesn't have that y prime to the other side. So I'm going to leave x dy dx as is, and then this is going to be plus y plus 2 times 4 is 8. 8 times 4 is going to be 32, so I'll have a 32x minus 2 times 1 times 4, so that's minus 8, and that's going to be equal to y plus 3, and I'm going to split this fraction because I only have my dy dx term on my right-hand side, so I'll put that as y plus 3 over y plus 3 squared minus x minus 2 times dy dx all over y plus 3 squared. Now again, I want my dy dx's on one side and everything without dy dx on the other side. So depending on whether you move your dy dx to the right or to the left, your signs might be a bit different than mine. However, the answer is going to be equivalent. What I'm going to do is I'm going to move my dy dx term to the left and everything else to the right. So I'm going to have x dy dx plus, I'm moving this entire term to my right hand side, so that's going to be plus x minus 2 times dy dx all over y plus 3 squared, and that's going to be equal to, I still have my y plus 3 over y plus 3 squared, which is really going to leave me with a 1 over y plus 3 when I simplify this down. And then I'll have minus y as I subtract this y, and then I'll have minus 32x as I subtract that, and then I'll have a plus 8 when I add that. So I know this looks a little messy, but it's okay, bear with me, we're going to work through this, and we won't worry about simplifying this down once we isolate that dy dx. So pulling dy dx out of both of my terms, I'm going to have dy dx times x plus x minus 2 over y plus 3 squared, and that's going to equal that entire right-hand side, which I'll write out quickly. Now what I'm going to do to isolate that dy dx is divide by my x plus x minus 2 over y plus 3 squared, because when I divide by that, it'll cancel out and leave me with just my dy dx. And again, this side also gets divided by it, so that's divided by x plus x minus 2 over y plus 3 squared. And so I don't have to write this out again, I'm going to go ahead and erase all this left-hand side and just write my dy dx. So my dy dx is going to be 1 over y plus 3 minus y minus 32x plus 8 all over x plus x minus 2 over y plus 3 squared. So this problem will be simplified down if you find common denominators among your numerator and your denominator and then distribute throughout. However, let's continue on for the sake of time. Moving on to our next part, just as we can take the derivative once, twice, 3 times, 4 times, getting that y double prime, y triple prime, and so on, we can take higher order derivatives when we're doing differentiation of implicit functions as well. So just as with explicitly defined functions, we can take the derivative multiple times to calculate higher order derivatives. However, we need to remember to plug in dy dx or y prime, our known derivatives. So we don't want dy dx. Still in our problem, we're going to plug in what dy dx is when we're solving for y double prime. And again, I want to note that we're taking the derivative with respect to x. So we're going to be finding the second derivative of y with respect to x. So let's take a look at A. Let's start by taking the first derivative. Taking the derivative of x cubed, that's going to be 3x squared. The derivative of y squared is 2y times dy dx. And then we have the derivative of 5x, which is just going to be 5. So what exactly is my first derivative? Let's solve for dy dx. dy dx is going to be equal to, I'll subtract my 3x squared to get 5 minus 3x squared. And when I do that, you can see that all I'll have left on my left-hand side is going to be my 2y. So then I'll divide by that 2y to get my final result. So it's going to be 5 minus 3x squared over 2y is equal to my first derivative. But I want to find my second derivative. So I'm going to take the derivative with respect to x again. Taking the derivative with respect to x of my left-hand side, d dx of my left-hand side. Think about what that's going to be. That's going to be my d2y over dx squared. That's my second derivative of y with respect to x again. How am I going to do that? Low d high minus high d low all over low squared, the quotient rule. So low, 2y times the derivative of my numerator is negative 6x minus high, which is 5 minus 3x squared, times the derivative of my denominator, which constant multiple rule, pull that 2 out in front. So we'll get 2 times, what's the derivative of y? That's 2 times dy dx. And that's all over my denominator squared, which is 2y squared. Now remember, like I said, we need to remember to plug in dy dx. We know what dy dx is. dy dx is 5 minus 3x squared over 2y. So we're going to plug that right on in, so that our function is just in terms of y and x, not also in terms of the derivative. So our second derivative of y with respect to x is going to be 2y times negative 6x, I'll write this as a negative 12xy, minus 5 minus 3x squared times 2 times dy dx, which is 5 minus 3x squared all over 2y. Remember, that is our derivative, 5 minus 3x squared all over 2y. And this is all over 2y squared, which I'll write as 4y squared. Now just to make this a little neater, let's cancel some things out in our numerator. We'll have negative 12xy minus 5 minus 3x squared multiplied by itself is going to be 5 minus 3x squared squared. So I'll write that as 5 minus 3x squared squared. And then this 2 will cancel out with the 2 that was multiplied by y. So that 5 minus 3x squared squared is all over y. And this is all over my denominator of 4y squared. Now, if you don't want fractions within fractions, I recommend finding that common denominator or multiplying by 1 over 4y squared as opposed to dividing by 4y squared, and then distributing it through to that numerator. But for now, and for the sake of time, I'll leave this as is. The important part to remember is that when you take the derivative implicitly, you can take the derivative again. To get that second derivative, just remember to plug your dy dx back in. Let's do one more example, example B. So taking the derivative of cosine of x, derivative of cosine of x is simply a negative sine of x. And then we're going to take the derivative of our right-hand side, e to the 3y squared plus 4. Remember, e to the f of x, that derivative is itself times f prime of x. So I'll just rewrite e to the 3y squared plus 4, but then what is the derivative of 3y squared plus 4? that's going to be 6y to the first times dy dx, remembering that complete derivative. D dx of 3y squared plus 4. That 4 is a constant and goes to 0, but this 3y squared, chain rule, 6y times dy dx. I cannot stress that enough to make sure you do not forget that y is a function of x when we're taking the derivative of y with respect to x. Now, in order to simplify this down, I'll get that my dy dx is equal to a negative sine of x all over e to the 3y squared plus 4 times 6y, or 6y times e to the 3y squared plus 4. And again, how I did that is I just divided by everything that dy dx was multiplied by in order to isolate it. So now, finding that second derivative, again, we're going to need to use the quotient rule. So we'll have low d high minus high d low all over low squared. Now feel free to either leave the negative out in front or put it with the numerator. I'm going to go ahead and put it with the numerator just so I can carry that on through. So I'm going to have low 6y times e to the 3y squared plus 4. So that's low times d high. The derivative of sine of x is going to be cosine of x, but remember that's a negative, so that's times a negative cosine of x minus high d low, so that's minus a negative sine of x if I left that negative with my numerator. Although I will say it's probably easier just to leave it out in front, so feel free to do either, times the derivative of our low, which we have 6y times e to the 3y squared plus 4. What are we going to have to do? Product rule, because we have one function times another function. So this is going to be first, which is 6y, and then we have to multiply that by the derivative of our second, the derivative of e to the 3y squared plus 4. We've already done this, but let's talk through it one more time, remembering the chain rule. We leave e to the 3y squared plus 4, then we multiply by the derivative of that inside function, which is 6y times dy dx. So that's first times the derivative of the second. Now we're going to add second times the derivative of the first. So we're going to add our second, which is e to the 3y squared plus 4, times the derivative of our first, the derivative of 6y, is 6 dy dx. And that is all over our denominator squared, all over 6y e to the 3y squared plus 4 squared. So I'm going to quickly just simplify down and making sure I plug in that dy dx, and I need to plug it in this case twice. So making things a little neater, I'll have the second derivative of y with respect to x is going to equal a negative 6y e to the 3y squared plus 4 times cosine of x minus the negative, so that will be plus sine of x times that entire quantity, that product rule we had to deal with when we took the derivative of the denominator. So 6y times 6y is going to be 36y squared. And we have that multiplied by e to the 3y squared plus 4, and that's all multiplied by the derivative of y with respect to x, which is our negative sine of x all over 6y e to the 3y squared plus 4. Now what I'm going to do to save myself some time and room, I'm going to cancel out in this step. So you can see this e to the 3y squared plus 4 will cancel out with e to the 3y squared plus 4, and 6y will cancel out with my 36y squared to leave me with a 6y. So this remains as a 6y. So I have negative 6y sine of x. And again, that's because my denominator from my first derivative canceled out with a 3y squared and a 6y to leave me just with 6y times the numerator sine of x, and that was negative. So even though it looks messy, it's going to simplify down kind of nicely. So we have negative 6y sine of x, and then we're going to add that to, again, we have e to the y squared plus 4 times 6 times, again, dy dx. So we'll have 6e to the 3y squared plus 4 times that derivative of y with respect to x, which gets multiplied by a negative sine of x all over 6y times e to the 3y squared plus 4. Again, my e to the 3y squared plus 4 will cancel out, and a 6 will cancel out to leave me with negative sine of x over y. So as opposed to adding a negative, I'll just subtract a sine of x over y. And that's all over my denominator squared, which I can distribute this exponent in because everything's multiplied together. 6 squared will be 36, y squared is y squared, e to the 3y squared plus 4 squared, distributing that exponent of 2 by multiplying it, we'll get e to the 6y squared plus 8. And there we have it. That's my last derivative on this example worksheet. And I know especially taking the second derivative can get quite tedious when doing it implicitly, and even when taking the derivative explicitly, it can get quite tedious with that second derivative, especially when dealing with the quotient rule. However, what I recommend is just making sure you're writing out each of your steps to help you simplify down, and don't forget to plug in that dy dx. But the big takeaway from this worksheet is that when you're taking the derivative of some function of x with respect to x, you need to remember to use that chain rule, whether you have y as some function of x or t as some function of r. If you're taking the derivative with respect to one variable, if it matches, you're all set. If it doesn't, you have to remember that chain rule. Now, what I recommend at this point in time is to practice those derivatives. You now have tons of different techniques and rules for calculating the derivative, so go back and practice. And once you've done that, continue on to the next video. But until then, good luck with your online learning.